Hello, astronomy. We're in my basement and we're going to attempt to do a lab today. We'll see how this goes. At the very least, we're going to demonstrate how this all works. So what I've got right here is an emission tube. We've got a gas of hydrogen inside this tube. There's not, let's turn so I can see at the light there. There's not very many molecules of hydrogen in there. It's very thin gas, it's almost a vacuum, and we're going to electrify that with some super high voltage and go ahead and cause the electrons that are on those hydrogen atoms to jump up and fall back down in their shells. And we know from previous times that when they do that, they're going to release some light, of course, right? So this is going to be in your lab books. If you can turn to page 20 is where this starts. It's called Cosmic Fingerprinting Spectral Lines Lab, and it goes all the way through to page 26 in your book where it says Spectra in the lab. So I'm going to kind of work through this with you, and then afterwards we'll post like a little short 5-question quiz for you to use your notes and answer. I would really recommend that you read through this first, because there's a lot of words that I wrote down here to help make this all make sense. I will work through the equations with you here in just a second, but let's see what these spectral tubes do here. So remember, this is an emission spectrum, which is the same thing as a bright line spectrum, and you're not going to see the whole color spectrum with this. So what I have... This is called a spectroscope, and I've tried and failed many times now to get the camera lined up with this. Oh, you can actually see a little bit of a spectrum right there. There's a diffraction grating on the front of this thing, and then you look through this, and it kind of magnifies the light, like we saw Newton doing, and you can actually read out where the lines are, the emission lines are, right across the spectrum, like how many nanometers the wavelengths are. So we're going to show you what at least the tubes look like. Let's turn the lights off here. Oh, got really dark. Might have got too dark. I can't see what I'm doing. Oh man, here we go. Almost got it. There we are. Oh yeah. So this is hydrogen. Hydrogen kind of gives off this really pretty, like bluish, kind of little bit of red in there, kind of a glow, and that is very specific to the jumps of those electrons, and when they fall back down they're emitting light, remember? So today's lab is really all about the nature of light and the quantum nature of light, as opposed to just the wave nature of light. Remember, light has two properties. It's both particle and wave, and we kind of have to just accept that. It's a weird thing, but we want to see why light only comes in certain discrete packets, and we're going to kind of play with that somewhat today. So I'm going to kind of flip this off here, and we'll put another bulb in. I think I'm going to turn my light on so I don't electrocute myself here. Kind of put that in the background. I think we'll be able to see it enough with that just kind of turn backwards. So this was hydrogen. Let's just put some of the other ones in there. I don't pull them out quick enough to get a little hot. This one here is argon, the gas argon. Go. Ooh, kind of looks pretty similar. It's got a really, really nice glow. Argon glows really well. Yeah, look at that. Flip that one off. And let's throw in, we have here helium, right? One of the other primary constituents of the universe. Ooh, look at that thing glow. Look at that. And I wish I could get this to work right. I don't think there's any possible way I can do it. I've tried so many times. You can sometimes just see it a little bit, but I don't want to stand here for 10 minutes trying to get this for you. Oh, you can almost just see some of the lines there. Not the white ones, the colored ones off to the side. Just barely. It's really hard to do. Yeah, I think it's a lost cause. But that was helium. Let's do another one here. Oh, need my light back on. Can't see what I'm doing. Okay. This one is Mercury. Now, Mercury is an interesting one. Look at that. Boy, does that glow. Pretty cool. Now, Mercury, the jumps that its electrons are making give off some really short wavelength radiation, short wavelength light, and so that's actually, some of that is actually in the ultraviolet. So I wouldn't want to stare at this for a real long time, because there is some UV light given off there. And we know that's not so good for the eyes, right? Give you a suntan too. So this last one is probably the best one. Let's flip this guy back on. Oh yeah, look at that. It's got a neon glow, because that there is neon. And you can't quite tell, it's so bright in the camera, but boy, that thing is just orange looking. It's really cool. And so that's what our neon signs are made out of. So we're going to head upstairs, where I'm going to attempt to transition over to doing some math. And we're going to bring our books up here with us. Let's see if I've got everything. So hang tight, because I can't seem to shut this video off without losing you. Not that savvy yet. All right, here we go. Going on a trip through my house. So we're heading back upstairs here. Here we go. We're going to set that there. A little stand set up here. Okay, so we're going to do some of the problems in here. And I just want to show you a couple of things, but please read this or it's not going to make a whole lot of sense. So, hold on one second. Okay, let's get this kind of set up here. Okay, so my pictures here are black and white, but it doesn't really matter. You can look up pictures on the internet if you like. What we're going to look at here is essentially one of the most basic quantum equations. So you are doing some quantum math here. It's the real deal. What we've got here, this first equation, is showing us the relationship between energy, okay, and the wavelength of light. And these things are inversely related to each other. So if you think about this, as the wavelength increases in size, its energy is smaller. As the wavelength decreases in size, the energy is greater. So shorter wavelengths carry higher energy than longer wavelengths. And that's not too surprising if you remember UV light, X-rays, that's some pretty powerful stuff. So we've got some stuff over here. I kind of defined the variables in the equation for you. Lambda here is the wavelength of the light, and it's going to be in meters, so we'll have to do a little converting. 1 meter is 1 times 10 to the 9 nanometers, which is usually how we talk about light, because the wavelengths are pretty short. Okay, they're pretty small. H here is the Planck constant, and it's just a constant, just like C is a constant, the speed of light. So those numbers are always the same, and they're right over here, 3.0 times 10 to the 8 meters per second. So that's in the same units here. That's why this is going to come out in meters. And Planck's constant, 6.63 times 10 to the negative 34 joule seconds. So we're going to mess with joules here as well, and we're going to have to do an additional conversion, because the energy value for this, for the electrons, is usually given in EVs, which is electron volts. So 1 electron volt is 1.6 times 10 to the negative 19 joules. So we'll make this all make sense here in a second. The equation is really pretty simple. It's just keeping the numbers straight, punching them in the calculator right. So I'll kind of do that along with you here. But remember, what we're essentially proving here and showing is the quantum nature of light. So what you couldn't see downstairs where I was trying to show you guys the emission tubes, here are all of the spectra that you would have seen. So rather than seeing the continuous Roy G. Biv spectrum of all the colors of the rainbow, hydrogen would have emitted just in these specific points right here. So one thing I want you to make note of specifically are right here. I'm not going to redraw these for you because you can just refer back to this page, but normally in the lab we draw all these in, we color them. So if you're thinking about this in terms of colors, right, 400 is smaller than 700. So 400 is a shorter wavelength, right? So is that going to be blue or red? Think about that. So blue is down here on this end of the spectrum where the short wavelengths are. So this is more blue stuff, and this is more red stuff over here. Okay, just so you can kind of picture it in your head. If you saw these, they would actually be colors. So why does hydrogen look the color that it looks when you excite its electrons? Because they emit specifically at these wavelengths, like exactly at these frequencies right here. And now down here, the scale at the bottom is in nanometers, so we can measure the length of the wave based on where it falls in the continuous spectrum, which is the rest of it that's missing. Helium, same thing. It's got some very specific spots here that it emits. Neon, which is just such a cool one. If you look at it, oops, sorry, I was talking about all that. I don't know if you could see some of it. So the hydrogen, the lines I was marking were these specific lines right here. Okay. Helium, and then neon, which is really cool. Look at all the different colors neon's emitting. They're down here in the reds and the oranges, and that's why neon gets that really cool color like that. It's emitting a lot of light in this region right here. Argon, which honestly the spectrum looks like a big smeary mess if you saw it in the lab. It doesn't look nice, nearly as nice and neat as this, but it's just really smeared, almost all the colors of the rainbow. And then mercury, it's got a couple of really strong lines that are super easy to notice, right? Right here, right here. So that's 500. That would be right about just a little bit before the 550 nanometer mark, okay? Then another one here, somewhere closer to the 575-ish region right here, okay? So these three lines are super noticeable. Those three lines are super noticeable, but it's not just that there's three lines, it's that they are precisely at each of those values, like they are dead on, and they will always be exactly right there, right? Unless, right, the object's moving towards us or away from us, right? So with the Doppler shift, I'm going off topic here, those lines will shift this way or this way. If the object's moving away from us, all those lines, we know where they're supposed to be, they actually slide this direction. And so we can measure exactly how far they went, and we know how fast the object's moving away. If they shift this direction, we can measure how far they went, and we know it's moving towards us. We know how fast it's moving towards us. So that's one way that we can figure out how things are moving in space and how fast they're going in space. So there's what we would have seen downstairs had we looked through the actual spectroscope. Now we're going to play around with this equation a little bit, see if we can understand a little bit about why this is doing what it's doing. So I'll flip the page over here. Okay, so I've got, wrong page. Okay, I've got another equation here for you and a little diagram. And this, hopefully I think you can see that okay. Yeah. Oops. You're going to be using this equation some, as well as the other one that I just showed you. Okay, and it will help you if you read through some of this stuff a bit. Okay. This E sub n here is the energy level of the orbit of the electron. Okay, so think of these n values, these n numbers here. These are the distance of the electron from the nucleus. So we're talking about hydrogen here, simplest element, right? How many protons, how many electrons? One proton, one electron, no neutrons. So if you're picturing this thing as an atom, this little diagram here, you've got down here somewhere there's this proton, right? That's got a positive charge. And then you've got this electron. And it's in this shell. Okay, it's at this level right here. This would be, say, n equals 1. okay? N equals 2, so this is as close as this thing can get to this nucleus. It wants to be close to this because an electron's negative, right? So in the first level, it's at the ground state. This is what we refer to as the ground state. So that's as close as it can get. If it absorbs some energy, it could jump, right? It could jump up to the next level. That's this N equals 2 level. So it would jump up this high at N equals 2, right? If it jumps from N equals 2 or from N equals 1 all the way up to N equals 3, that's a big jump. That's way up here somewhere is N equals 3, right? N equals 4 up here, right? N equals 5, 6, right? Right on up. Now at some point, remember, this electron can absorb so much energy, which is what this little infinity sign is right here, that it will free itself entirely. It's going to ionize. It's going to just take off and go zipping away like they exist in the sun. So we can do some calculations to figure out exactly what wavelength of light is going to be absorbed and emitted and how much energy is moving around in there with this equation right here. So what we've got here, trying to remember what I'm doing here, if you look at this, okay, for an electron to jump from N equals 2 to N equals 3, it has to absorb a very specific packet of energy, okay? And conversely, when it falls, it will re-emit exactly that same packet. So we talked about that some in class, which brings me to these numbers over here, these electron volt numbers, okay? This is the energy that would be required to completely free it. So if I hit this guy down here at N equals 2 with 3.40 electron volts, this little electron, this down here at N equals 2, will take off and completely leave the nucleus. It's not coming back. It's zipping away entirely, totally free. Okay. Now, why is that number so much bigger than these numbers up here? Well, remember, the closer it is to the nucleus, the more tightly bound it is. The further away it is, the easier it is for it to escape. So think about like magnets here. This is a negative, this is a positive. They want to be together. You get them close together, and they feel that force really strongly, that electromagnetic force. But if you get them farther away, they don't feel the force as strongly, right? So less energy will zip it off further, okay? But now remember this too. If an electron is way up here and it falls from way up here, it took a lot of energy to get it there from way down here. If it falls from here all the way down to the bottom, it is going to give off a tremendous amount of energy. It's got a long way to go. It's got a lot of energy to give up to get itself down close to that nucleus, right? So that's kind of one way to think about it a little bit as we go. And some energy levels aren't shown here, like N1 isn't here, and N equals 6 isn't here. We're going to calculate N equals 6 here in just a second, okay? So you can read through the rest of this. I would suggest it. I think it'll make some pretty good sense to you now once I've explained that a bit. Let's flip this guy over. And we're going to kind of keep referring back and forth to all this. Here's a picture of some different types of spectra. The continuous spectrum, right? If you were looking right at the black body, you'd see Roy G. Biv, all the colors of the rainbow. The emission spectrum, the bright line spectrum that we've been talking about, this is what you would have seen through those tubes. It's a thin gas. It gets excited. Electrons jump up, fall down. They only emit at those wavelengths, right? An absorption spectrum is when you've got a thin gas sitting in front of something that's emitting the full spectrum. So it's going to absorb and then scatter those things that would have made those lines. And so you'll see black lines. You can't see it on that picture very well, but there would be dark lines in here where there's parts of the spectrum missing. And we talked about that in class, so you remember that. Okay. Whew, wearing myself out here. Let's go over to the procedure. So basically we worked through this. We did all of this downstairs. We kind of tried to see those. What we would have been doing is we would have been coloring in our spectra for all those elements. And I showed you all those elements, but remember, you've actually got in here a really nice picture. I know it's black and white, but all you need to know are the values the lines are at. You'll be able to answer the questions on the quiz if you look precisely at the values. They're going to be doggone close, right? It has to be, or it's the wrong element. Okay, so normally that's what we would do here, and we would color these in but we're not going to do this because it's a whole bunch of extra work, and I don't know where all those lines are unless I look them up, so I can't see it. The sun here, it would be a continuous spectrum, and normally we'd color this. Remember, 400 nanometers, this is going to be towards the blue end of the spectrum, right? And this is going to be towards the red end of the spectrum. So longer wavelengths, redder, shorter wavelengths, bluer. Where do they have more energy? These guys up here have more energy than these guys down here. Okay, so shorter wavelengths in that equation have the more energy. Okay, let's put this through here. Now, into the questions. We were supposed to look at a fluorescent light. We could have done that, but you wouldn't have seen anything because I didn't have a diffraction grating for you to look through. But you would have actually probably seen, had you looked in there, a little bit of mercury, along with some other elements. But yeah, they do put some mercury in there. It makes the lights really light up and glow really nicely. So fluorescent lighting can be a little bit harder on your eyes, right? And people do say that. It is true. And you're not going to damage your eyes unless you're staring directly at the fluorescent light all day. It's reflecting off a surface, so it's not nearly as hard on your eyes. Okay, let's see here. First equation. What is the energy level, E6, for an electron in orbit n equals 6? So it's at the 6th step up from the nucleus. And how much energy is given off if this thing jumps to orbit, or I might say falls to orbit n equals 2. It's going to fall back down. It's going to have to give off energy to fall down. So let's go ahead and work this out. We're going to need one thing from the front. So remember, all the way back to the front there, I'm going to try and find it, where I said that 1 meter equals 1 times 10 to the 9 nanometers. So think about a meter bar. Okay, a nanometer is 1 times 10 nanometers would equal 1 meter, right? It takes a lot of nanometers to make a meter. They're very small. Okay, here we go. So this first one, the equation that we need here, is the equation from right here. Okay, so what we're trying to calculate, remember, I'm trying to get all this stuff in here. We know n equals 4, we know n equals 5. We want to know n equals 6. So at n equals 6, okay, we want to know what's the electron volts for an n equals 6. How much energy does it contain, okay, at n equals 6? So we're going to run this calculation. I'm going to rewrite this equation here. That way you can see it. There's going to be a question just like this on the quiz, so as long as you figure out how to do it here, it's going to be simple. Okay, I'm going to write the equation again. Okay, n squared. Okay, let's plug in our values that we have. You can see that. Yeah, good. Okay, our values are, this is the same. Electron volts, it's always going to be 13.6 electron volts there, over N2. So that right there, we're trying to solve for n equals 6, right? That's where that's coming from. So n equals 6, so 6, and I'm going to square that. Okay? So this is a pretty easy equation to work out here. Let's do it on the calculator. See if you can see that there. See it? Yeah, there we go. Perfect. Okay, so we have 13.6 divided by 6, and we're going to square that. Okay, so that was 6 times 6, hit equals again, and now we have our number. Okay, so get that over there. That's my value. We'll go out to the same sig figs that they gave us there. 0.38 electron volts. Okay, so that's what n equals 6 is, 0.38 electron volts. I'm going to go ahead and write that on that page we just came from, so that we've got it. 0.38 electron volts. And it, there we go, should fit right in there. 0.38 electron volts. Good. So this should make sense to you. This is the amount of energy required to free that electron. If it's all the way up here at 6, level 6, it's only going to take 0.38 electron volts to send it zipping away entirely, right? But if it was lower, you'd take a lot more energy to kick it off completely, right? Or it's just going to jump up to a level. So there we are at n equals 6, but the rest of this question wants us to answer how much energy is given off if it jumps down to n equals 2. So it's going to fall from n equals 6 all the way down here to n equals 2, okay? Not all the way to the ground state, but to n equals 2. This is really tough math here. You know what you're going to do? All you have to do is subtract. So that's 3.4 electron volts. Check it out. 3.40 electron volts minus 0.38 electron volts. And if we plug that into the calculator, we're going to get 3.02 electron volts. Okay, and that's how much energy is given off, right, when it falls from 6 to 2. Right? We just did quantum math here. It's pretty simple stuff, isn't it? So now let's do this next one here. We've got an electron that's jumping from n equals 3 to n equals 2. Okay, so it's going from 3 down to 2. That means it's going to give off some energy. It's falling from a higher to a lower state. So how much energy in electron volts is given off? What wavelength is the energy that's emitted? So this first part is pretty easy, right? If we're falling from 3 to 2, all we've really got to do is subtract. But we have to know our numbers. 3, n equals 3, is 1.51. Can't see that, sorry. N equals 3 is 1.51, and n equals 2 is 3.40. So all we're going to do is subtract those two things, but that's where they came from. Okay, so n equals 2, get to where you can see it, is 3.40 electron volts. N equals 3 is 1.51 electron volts. I'm going to subtract those guys. We should get 1.89 electron volts. Can you see that? 1.89 electron volts. Yep, you can see that. Okay. So now the next thing that we need to do is we want to figure out the wavelength. To calculate the wavelength you're going to get from this, we're going to have to flip back to that original equation that I showed you. Yeah, this guy right here. So remember, it's easy to work, but there's going to be a lot of converting going on here. So we're going to have to keep referring back to some of these numbers. I'm going to rewrite the equation. So the wavelength that we're after, okay, is lambda here equals Planck's constant times the speed of light divided by E, the energy. Okay, well, we just figured that out. So what we have here, the two constants, let's plug those in. So this is, I'm just going to put equals here because this is the wavelength equals this, which equals what I'm about to do here. 6.63 times 10 to the negative 34 joule seconds. Okay. We're going to multiply that times the speed of light. That was Planck's constant. 3.0 times 10 to the 8 meters per second. Okay. Now we've got to divide all of that by E. Well, we just calculated E, didn't we? But there's a problem because this E, 1.89 electron volts, happens to be in electron volts. And the rest of our equation's in joules. So we need to fix this, and we're going to fix it by multiplying by, and that number, this number is right here. 1 electron volt is this many joules. So if you need to look back to that, it's right there, but it's not going to change. You can use it on the test or the quiz. Okay, 1.6 times 10 to the negative 19 joules. That's joules. Erase doesn't work. Trying to put my units on there for you. Do good math. Joules. There we go. Okay. Now all that remains is to push some buttons on the calculator. Let's make this happen here. If I can get that to where you can see everything. Okay. So you can use the storage button, or you can use parentheses to do this, or you could write the whole thing down, which sounds like a pain to me, but I'm just going to type it out. 6.63. Now remember, when you're doing scientific notation, it's the EE key, right? I don't put times. 6.63 EE. A little exponential comes up. I want negative 34. Okay. I'm multiplying that times 3.0, well, it's just 3. I can put the 0.0 if you want, but it doesn't matter. EE, 8. Right, I didn't put the times in there. Okay, I'm going to hit equals. Okay, there's the product of my first part of the equation. Now I need to divide. So I'm going to hit divide. So here's the part where you could have stored that number and brought it back afterwards, but I'm just going to divide, and I'm going to use parentheses. So I'm going to put some parentheses. I'm going to put this whole bottom part down here in parentheses so I don't get it screwed up. 1.89. If this confuses you, just do the bottom part first, do the top part, and then divide your numbers. Okay, times this, 1.6 EE, negative 19, EE, negative 19, okay? And now I need to close my parentheses, okay? So that just multiplied those two things together. I need to hit equals to get the rest of this. There we go. Oh, that's a heck of a number, isn't it? So what you're looking at here is the answer given in meters. So this is actually a perfect number, but we need to convert it. And my calculator is actually rounded here a bit, which is going to be a little confusing unless I plug in the conversion. So what I'm going to do is I'm going to multiply this number, which is in meters, okay, times 1, let's see here, 1 to the EE and 9, okay, and we have 6.5 or 657.7 nanometers is my answer. That's nanometers. So if your calculator does this rounding thing on you, you're going to have to multiply, because on the quiz I put it out to 1 decimal place there. Okay? So you'll have to multiply through all the way like I did. You can't just count over. I could have counted over. I would have got 658. And I don't know if you'll get it right unless you go ahead and multiply it through. But to get this, what I did is I took my, I'll write it down here for you. I took my answer. Answer comes out in meters. Okay. Multiply answer times 1 times 10 to the 9. Okay. So remember, use your EE key there. Don't put times, right? So to put it into that again. So 657. Well, I don't know if I can actually do that. I make a mess with my calculator because it's rounding. So just remember, you need to put 1 EE 9 times your answer, and that will convert it all the way through. Or you can probably figure it out. I mean, 658 is pretty darn close to that, right? So anyway, remember, your answer is going to come out in meters, and you need to convert it to nanometers because that's what we're talking in. All right, next question. What kind of light does a hydrogen atom give off when an electron jumps from an orbit with n is greater than 1 down to an orbit of n equals 1? Is that light visible or invisible? Well, let's check this out. So if we take a look over here, this is kind of an interesting question. Let's see. Let's look at our diagram here again. So what we're saying is, what happens if this electron, regardless of where it is, falls all the way back down to ground state n equals 1? It can't get any closer than that. It hits all the way to n equals 1. Well, the biggest release of energy would be if it fell from the top all the way down, right? But let's say that it's only like at n equals 2. So let's take like the smallest possible scenario here. So we'll say it's going to go from n equals 2 down to n equals 1. And so let's just kind of work that out and see what we get. Okay, so n equals 2 is 3.4 electron volts. Whoa. Okay. Yep. Okay, there we go. Okay. Okay, so if our energy level is, where are we at here? All right, there we go. So at En2, okay, and at En1, is 13.6. Now, if you're wondering where I got that from, that's right here. Oops. This is the reason that we're using that number right there. Okay, so all we're going to do is subtract here to get these, what the difference is. And I ran out of room. But if I subtract the difference here, I'm going to end up with 10.2 electron volts. Okay, I'm just getting rid of the negative there. I subtract the other way around. So 10.2 electron volts, subtracting. Okay, so now let's work this out just to spitball here, just like we did up here, to figure out the wavelength. All right, same exact equation I just used. Let's do it again for practice. So these two numbers are the same. So there's Planck's constant times 3.0, 10 to the 8. There's my speed of light. Okay, and we're going to divide by, there's my energy given off. Okay, 10.2 electron volts times my conversion for the joules. That'll be the same each time you're working with this. Okay, and let's see what we get. And remember, our situation is going to be similar. Our answer is going to come out in meters. So we've got 6, can you see that? There we go, 6.6. There we go, 6.63 EE negative 34 times 3 EE 8. Close that. And use my division, and then parentheses 10.2 times 1.6 EE negative 19 in my parentheses, and then hit equals to finish the division. And the number looks crazy again, but remember, we're moving this thing over 9 places. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 122 nanometers. Now, that's not that my calculator rounded that bugger again. So let me just go ahead and hit times 1 EE to the 9. So I'm just going to move the decimal place over, and it'll show me the rest of those places that we're missing. And there we go. 121.9, if I round, nanometers equals 121.9 nanometers. And that's my answer there. Okay, now where's 121.9 nanometers? Well, if we were to look this up, which I usually show a graph of it or a diagram of it in class, 121.9 nanometers. I don't really even need to pull it up any further than this. If somewhere around 450-ish, I think, is where you can still see blue light. After that, it, of course, is the UV, right? So this thing is shorter than 400 by a lot. This is some UV radiation right here. So if we're asking, is it visible light? Is it invisible? It's definitely invisible. It's definitely UV. We're talking about UV light there, right? At least I believe that falls in the UV part of the spectrum. It's definitely shorter than blue light, right? It should fall in the UV portion of the spectrum. Okay, so let's just kind of gloss through these last things here. How do the atoms and molecules create spectral line emissions? What's happening is they're absorbing, the electrons are absorbing very specific wavelengths, packets of light. This is what we mean by quantum, a quantity of light. They're jumping up, and then they're falling down and re-emitting an exact packet, an exact quantity of light. And that's how you get those different lines. So think about how complex the electron configurations could be on an atom. Most atoms have an awful lot of electrons, not just one. Not to mention molecules, which are atoms bonded together, have even more electrons that could jump into totally different configurations. So even though they absorb very specific packets, there's a lot of variation there. And we can tell exactly what we're looking at based on what wavelengths are emitted. Okay, what advantage does studying spectra have over direct imaging of an object? So, what if we take a picture of the sun? Yeah, it's great. We could take a picture. We could even direct image a UV image of the sun. We could image a radio image of the sun. We could image X-ray image of the sun, false color it so we could see it. We can see all kinds of structures and cool things. But studying the spectra, what does it do for us? It lets us know exactly which elements, exactly which ones are present. And then if we look at the lines, we can use those to understand Doppler effect and know how fast the thing is moving, if it's moving towards us or away from us. So it tells us a tremendous amount about the object, more than just maybe an individual picture of it would tell us. Okay, and this last one gets you thinking a little bit about exoplanets. So thinking about planets, maybe that aren't even in our solar system, but are in other solar systems, how might this be useful? Well, if a planet has an atmosphere, it would be really kind of keen to find out whether the atmosphere has oxygen in it, because we know oxygen's a pretty big signature for life, at least photosynthetic life, right? So if we find gases like oxygen in the atmosphere of a planet, that's a big one right there. And how do we do that? Well, it's tricky, but if a planet's passing, if it's big enough, it's passing in front of its star, and we can catch it in the right position, the light's going to pass through the atmosphere of the planet, and we can possibly study some of those spectral lines to figure out what kind of gas is in the planet's atmosphere. So it could be useful in a lot of ways. This last page, like I said, don't worry about trying to do that. We were just going to draw the pictures. So what do you need to know for the quiz? I would definitely make sure that you refer back to, where is it at? This page right here, because it's got all the spectra. They're all listed. It tells you what they are. Right? You could just look at this. As long as you've got the right number, you got the right element. Okay. Other things you're going to need to know how to do. Let me just glance at the quiz for a second. You're going to need to know how to work both of those equations that we worked. One is literally as simple as just subtracting, right? We just do a little simple subtraction. We can figure out how much energy is given off. Another one is, calculating which exact wavelength is given off. So you kind of have to do two steps there to figure out how much energy you're moving by the electron falling down, and then plug that into the equation, right? And out comes your answer. Remember, you've got to convert. It needs to be in nanometers, not meters. Okay. Other things you'll want to know. Remember, this lab was entirely about the property of light that shows that it is a particle. Like it is a particle, not just a wave. Waves come in any length, right? But particles are discrete little packets. Think about the experiment that I did in lab for you, where I set up the can and we hit it with a bunch of different types of light. We had it was static on the can, and the electrons were repelling each other, and all the little foil pieces were pushing apart. And then when we shot it with the mercury lamp and hit it with just the right frequency of UV light, those electrons absorbed that UV light and they zipped right off. We shot them clear off. We ionized them. We kicked them completely off. kicked them completely off their atoms. And then, of course, the foil stopped repelling itself, and it all fell back down, which was kind of neat. So, anyway, I think we did a pretty good job. You can use that. You can do the quiz, and you guys have a good day.